Welcome back to CPP Under the Microscope. Today we are pulling back the curtain on the oldest part of C++ toolchain, the preprocessor. You have used hash pounding code and probably written a few simple macros, but the preprocessor is far more than a search and replace engine. It's a transformation machine capable of generating code, simulating loops, and even writing its own macros. There we're going to unmask it. We're going to generate enums and string tables from a single list, write assertions that know their own file and line, glue tokens together to fake generics, build fake loops, evaluate arithmetic at compile time, inject compile pragmas from inside macros, and most importantly, we will look at the expanded output. Because the preprocessor is not magic, it's deterministic token transformation engine. And if you don't know what it expands to, you don't understand what you wrote. X macros are a way to keep data and code in perfect sync. You have a list of colors defined once as color list. By repeatedly defining a macro named X in different ways, we can generate an enum and a corresponding string array from the same source list. Let's look at the preprocessed output. When we run this command, we see the enum becomes red, green, blue. The trailing comma is harmless in C++ and actually makes code generation easier. Then we redefine X to hash pound name here, and we got an array of string literals. Here they are. One pitfall, you must undefine X between uses. Otherwise, the second definition leaks into the first. Always clean up your macros. Next thing is assert macro that captures context. Alright, this is the example. Let's run the compiler to check the preprocess output. Now we're going to see quite a lot of text, but that's because of the encode here. Here is our assert macro. As you can see, it evaluated and the preprocessor figured out which file, which line. Here is something a function can do, capture exact source location of its call. The assert macro uses the stringizing operator to turn the condition expression into a string literal, and the predefined macros file and line to pinpoint where the assertion fired. When we expand it, we see the condition text, the file name, and the line number all baked in. This is incredibly handy for debugging. But notice the do while wrapper. Without it, writing if x assert y else would break because the macro would expand to an if without braces. The do while 0 is a standard trick to turn a multi-statement macro into a single compound statement. A word of caution, the condition count is evaluated every time it appears in the macro. If you pass something like plus x, it will be incremented here in the if condition, and potentially everywhere else that condition is used. Here we stringize it, so it won't be evaluated here. But for example, if we do this, we create a variable x. Let's check the output. Here, it will be evaluated here once, and then here in the printf function call. This is a classic macro pitfall. You have to be careful about that. All right, next thing we're going to take a look at is token pasting. Let's write the example for it first. All right, let's run the compiler to check the processor's output. Here is the output. Before templates, C programmers used macros like this to simulate generic functions. The token processing operator concatenates max with the type name, producing a unique function name for each type. When we expand generic max int, the preprocessor literally writes the body of the function that works on ints, and the same for doubles. It's a primitive form of code generation. Today we would use template, which is type safe and doesn't pollute the namespace with dozens of function names, but you still see the token parsing operator in macros that need to generate identifiers, for example, in large frameworks that define service interfaces or in low-level C libraries. Here is the output. As you can see, we have two functions, and the preprocessor just wrote them for us. All right, next is Variadic macros and VA opt. Let's start with writing the code first. And let's compile and see the preprocessor's output. Here it is. As you can see, this is the first one here, and we pass it parameters, and it produces it properly with comma and the number here. Then we use the walk save, which basically does the same thing. The difference is walk save, I can pass it only one argument without parameters, and it will skip the trailing comma here. This option here basically says if var args is empty, just don't include the comma. And in this example, we don't have that option. If this is empty, the comma will be added. As you can see in this example here, yeah, we have trailing comma and no parameters after that, so this will not compile. VA opt is something that can be used when we have trailing commas that might become problematic. Now, the next thing we're going to take a look is macro recursion. Let's write the code for it. All right, so this is the example. Now let's check the preprocessor's output. And here it is. Now, what's actually happening? So we define repeat one macro with x, and it expands to x brackets 1. So that's basically another macro. Then we define repeat 2 that expands to repeat 1, Then you have repeat 3 that expands to repeat 2. And obviously repeat 2 will expand to this, and repeat 1 will expand to this. So in the end, we'll have x1, x2, and x3. Then we create macro declare lm, and it expands to this int lm, and we append to it I, and this is how we use it. We have this macro here that picks the correct repeat from these three. We have to obviously, if we want more, we have to add more repeats. So next one, for example, repeat 4, repeat 5, etc. We know how repeat 3 will be used. Now let's just do it. Let's just substitute it here. So we know that this will be expanded to this. So let's just write it down here. We know that this 3 will be like so, and this will be this one. So this will expand to this one, and then preprocessor will take this thing and expand it with this. So it will be like so. Obviously, x is replaced like this. On the next iteration, it will see repeat 2, and repeat 2 is this thing. And we see repeat 2 here, so we substitute it like so. Declare lm is placed like so. Then we see repeat 1. This is repeat 1. It's substituted to this. We take it, and here it is. And at last step, declare lm is actually this thing. So we see declare lm, and it will substitute it this way. It will be like so. Declare lm with 2 will become this, and with 3 it will be this. Yeah, and that's the output that we see here. As you can see, that's almost like recursion. It's not really. It's a way to simulate loop, but it's not really that as well. You can't really have a macro call itself directly, but you can chain macros to achieve fixed amount of iterations, as we saw. This is a limited form of compile time generation. It's used in libraries that need to generate repetitive boilerplate, like serialization, frameworks. It's fragile. You have to define a separate macro for each count you need. It's good to know. It's good to understand it and to be able to read it when you encounter it in the wild. So next thing is conditional arithmetic. Let's clear this example and write it. The preprocessor can do more than simple hashtag defines, hashtag inf, etc. It can evaluate integer arithmetic, including comparison, logical operators, and even bitwise operations. Here we can check version is at least 200, and the minor version, the last two digits, less than 50. When we set version to 203, the condition holds, so feature new is defined as 1. We change it to 250, and it fails, and feature new is set to 0. And I need to spell feature new properly. We can also issue compile time messages with hashtag error or hashtag warning. This is useful for sanity check, ensuring a required macro is defined for a version is defined or a version is compatible. the preprocessor stops immediately on error, which can prevent cryptic compiler errors later. We can see that the compiler will give us a warning during compilation. Next, we'll talk about encode guards versus Pragma ones. Let's write the code. We create a small header file, main.h. We added the encode guards. And in main.cpp, we'll encode it. Now, let's run the compiler to get the preprocessor's output. Obviously, nothing happens because this thing will, all this will disappear. Now, let me just, here is the function that we included in the main.h file. Here is the main function. Let's use Pragma once and check the output. As you can see, it's the same output. The if and if is standard. Pragma once is a common extension that's simpler, but not technically standard, though widely supported. So which one should you use? It's mostly a style choice. I'd say Pragma once is fine for most projects, but if you need absolute portability to obscure compilers, stick with the if and if header guards. Alright, the next thing we're going to check out is injecting compiler instructions. Let's check the code. I need to introduce a variable that's unused, for example, int x, and compile with warnings. Let's see. As you can see, it says unused variable x. So the way we use this defined here, this macro, we add it here, and now when we compile, it doesn't produce this warning. Now let's check what exactly it produces. Basically, it adds this Pragma directive, tells the GCC to ignore a unused variable, and as you can see, it does just that. It doesn't produce this warning. Sometimes you need to suppress compiler warnings for a specific piece of generated code, but you can't put Pragma directly inside the macro because this symbol has a special meaning in the macros. The Pragma operator takes a string literal and turns it into a Pragma directive. Here we define suppress warning, which stringizes argument and passes it to Pragma. Then no used var is used to suppress the unused variable warning for GCC. When the macro expands, it becomes to this thing here, as we saw. This is a powerful way to make macros more robust. They can tweak compiler behavior exactly where needed. We've seen the preprocessor at its most magical, generating enums and arrays from a single list, capturing source file locations, creating generic functions, simulating loops, and even injecting Pragmas. But with great power comes great responsibility. Macros ignore scope, they can evaluate arguments multiple times, they offer no type safety, they make debugging a nightmare because the code you see isn't the code the compiler compiles. Modern C++ give us templates, const expr, inline functions, static asserts, and attributes that do the same job more safely. So use them. If you must use macros, for example, in logging or assertion macros that need the file and line, keep them simple, wrap them in a do while, and always test the expansion. That's the preprocessor Unmasked. If you enjoyed this deep dive, hit subscribe and ring the bell. We've got plenty more C++ coming your way. Leave a comment with your favorite macro trick. Till next time, keep your tokens pasted and your expansions clean.